find a metal plate. Just put a metal plate. Oh. Get something out of metal. Like iron.
Oh, yeah, just the closest thing that I have that really magnetizes that is a giant lamp I have.
There you go.
You just have to put the lamp outside and then take it out.
See, people are still recovering from Monday. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Welcome to EE123 lecture 14. Woo! Woo! Today's my favorite topic, sampling. It's my favorite topic. Every time I just go through, I realize, wow, I love that stuff. Yeah, before we get this on the way, a few announcements. Lab 2 is due Thursday, right? Okay. Anybody has an EpiPen? Okay. Lab 2 is due Thursday. Any issues with Lab 2? Yeah.
I'm trying to load the real-time part, but after downgrading, the locate numbers won't work either. So I get the Google Maps mode, but not, it won't actually record anything. I don't see it in my terminal like you did. I'm assuming I'll follow the radio because if it were,
Come over to lab, and we'll sort all of these out. Anything else? Anybody else having issues? Have you playing with the SDRs a little bit? Yeah, these are quite a bit of fun. Be careful; you might spend many hours of your life with these. Spend that. Okay. One thing: amateur radio exam, March 16th. Remember, in order to do Lab 5, you'll need an amateur radio license. Okay, and it's part of the thing that we do in class. If you want to get credit for this, register for the class. I don't know if you can even anymore, but no, it's past that, right? So it's done. So, but you can still take the exam. Today I'm going to have office hours at the Ham Shack 5 to 6. I'm going to anybody who wants to play with digital modes is more than welcome. And from 6:30 to 8, I'm going to finish early today, talk about digital modes and repeater operation. I'm going to hand out radios. I'm going to play with talking through repeaters. So if you want to practice that, you're welcome to come, even if you're not taking the class. Start thinking about projects. I'm not going to talk about it too much. Just say that you should start thinking about it. We're going to probably have what's called a default exciting project, but maybe a competition. But you can also be creative and create your own project. And we'll work on that. We'll talk about this later. Any questions except for the project where I'm not going to answer any questions about it? How's the midterm? It's good? It's okay? Was it easy? Really? That bad? Okay. Well, try to do my best. You should have. I hope you did yours, and then I think we'll meet somewhere together. Okay, so today we're going to talk about sampling. The question is what is the following phenomena I'm going to show you? I'm going to show you two videos. This is one video. I'm going to show you another video of a helicopter crashing. Right? It should be crashing, right? Because propeller doesn't work. Right? Yeah, all the lift it gets from the back propeller. Oh, it just rotated a little bit. Isn't that amazing? So obviously something's wrong here, right? Obviously that's not what's going on. And the reason that you're seeing this propeller just standing in the air like that is because we take a digital photo at a certain rate, or digital video at a certain rate of frame rate, when we take a picture of this really fast-moving blades. And so there's implication of taking something at a certain rate if you want to measure something that's real life, that is actually continuous. And the implications are that we need to have a certain rate such we can capture things that are moving really fast. And there's going to be kind of a criteria that we're going to get to of what would be the rate in order to be able to reconstruct that dynamics. But at the same time, if we don't meet that rate, then we get a phenomena which is called aliasing, in which certain high frequencies pretend to be lower frequencies, just because you're not sampling at the right rate. Okay? So this phenomena is very interesting. Now the question is why would you want to do sampling at all? And this is all chapter 4, so it's actually quite a long chapter. We're going to spend a couple of weeks on this. And really, sampling is all about converting continuous time, which are non-quantized measurements, often, non-quantized measurement, into discrete times, which are usually quantized, because we're going to represent them on a computer with finite precision, okay, not infinite precision. And then there's the counterpart to sampling, which is the reconstruction, in which you take discrete time signals, which are quantized, and you make continuous time signals, which are not quantized. Give me an example of reconstruction. This is a reconstruction. What you're staring at it is a reconstruction. These are bits on my computer that are creating a signal that is through this cable. Actually, there's some analog to digital to analog conversion that's happening here. I think at this thing. Here there's analog signals going, and those are being displayed as light onto the screen. Okay? So this is another form of digital to analog conversion. Okay? So, and of course, if I had a certain resolution of text that I want to present, I might not be able to represent it on this particular screen because it doesn't have that ability to do so, and so on and so forth. Okay? So as I look actually very close, you can actually see the discretization of the pixels. If you come by afterwards, you can actually see the pixels, which is kind of cool. Okay, so why do you want to do this? I mean, obviously, it makes a lot of sense because anything that we do today in the digital world is related to capturing our analog world and converting it into digital, right? We convert audio, photos, videos, all sorts of stuff that we collect in our world. People are now collecting other information, like healthcare information. So Fitbits, they measure all sorts of stuff, like how much you sweat and what's the temperature and what's their heart rate and so on and so forth. That's all being then collected as well. Of course, digital communication, whether it's wireless or wired communication or optical and so on and so forth. If we want to do any processing, if we have samples that are representing on a computer, we can actually do this much easier than we could do it in the analog domain. If we want to create something like computer graphics, there's a whole, there's going to be a whole slew of new technologies that kind of come up, which are virtual reality and augmented reality that you're going to be seeing quite soon. And so all of these will be rendered onto the physical world somehow, right? And then, of course, if you want to do anything that's related to detection, classification, data processing, data mining, and so on and so forth, once you collect data into a digital mode, into values, then you can probe them. So if you think of an analog to digital converter, like how common they are, let's look at this device, right? How many analog to digital converters are in this? Several. Actually, it's probably hard to say, but we can kind of do the trivial thing. Okay, it has Bluetooth. Okay, Bluetooth chip probably has a to D. Okay, what else? It has a wireless Wi-Fi, right? It has a Wi-Fi. Actually, it has two Wi-Fis because it has 2.4 and 5.81. Okay, it has a cell phone. It has actually the cellular one, which is probably 4 radios, depending on the bands that you are working on. All right, so these are just the radios. Okay, what else?
If you have multiple antennas in it, do you need a separate converter for each Wi-Fi antenna?
Yeah, probably there is actually a separate one. And if you actually do phased arrays, like all these do over here, yeah, absolutely, you digitize each one of the channels. What else? What else there's here that? Touch sensors, right? Like the touch screen, right? Converts where you touch into digital, and it has actually quite a bit of them. Microphone, yeah, that's a good one. What else? Camera, a couple of them, right? Couple of cameras. A gyro, accelerometers, compass, yeah, that's another one. Compass. Anything else? Yeah, it has actually temperature controls, right? So it measures its temperature. What about current regulation, right? So all of that could be, I don't know if actually is done by A to D or not, but probably it is because you can measure the battery and so on and so forth, right? So you measure that. So there's tons of stuff. There's, digital to analog to digital converters here. And of course there's digital to analog converter as well, right? It has the speaker, it has the screen. What else? It has like a few speakers, and I think it has the radios, of course, and so on and so forth. Okay, so tons of it just in a single device, and then this one as well, and there's just many of them that you can think of, right? So this is a huge thing in terms of technology that's used today. So let's just look and try to analyze those systems and figure out what's actually going on. So if you look at a typical system, which is an analog to digital converter and then digital to analog conversion, you've got a signal, and this we're going to develop here a terminology that's also used in the book. Okay, so pay attention. You got a signal which is continuous time, x sub c of t. It will go through some analog anti-aliasing filtering. There's always some analog anti-aliasing filtering going on. Okay. Often we'll go after that through some amplification. Maybe the amplification is going to be before, maybe it's going to be after, maybe there's before and after. There might be some regulation as well in terms of signal intensity. We're going to ignore all of these right now. We're just going to think of just as a passive filter that's in the analog domain that the signal is going to go through. And then you got yourself the conversion, which is, we call it an ADC, or an analog to digital converter. That is going to be made out of something that will sample your measurements. So at at discrete time, so t equals n times t, this is the sampling rate, the interval between time points. This will give you a signal, which is x of n, that is equal to x sub c at times n times t, so at discrete points. Then we'll go through some quantization. Again, this is a model. This is not actually how it's implemented, of course. It is a model that we're going to then be using in order to analyze those systems. Then it will go through some quantization. That's 8-bit, 16 bits, 32 bits, whatever you pick. And then now you can do discrete stuff on it. Now this is stored on a computer. Now you can process it, do cool DSP, storage, compression, processing, whatever you want. Then you're going to come out with a signal that comes out of that processing. And then you're going to perform a reconstruction, which is the digital to analog conversion, or D2A, in which you will get back Y sub C of T. Okay, this is a whole system. Okay? If you think of the one of the exam questions, the one that I had, right, when that was quite a complex system, where you generate something on a computer, which is completely digital. Then you do digital to analog conversion displayed on a screen. Then you do analog to digital conversion by taking a picture with a camera, and then you do processing on it. So it's kind of like reverse to this one. Okay. And how many of you take pictures of screens? Every once in a while, like whenever you have, oh, this is a cool talk, right? That's a cool slide. I'm going to take a picture. Right? Quite often happens. Okay. So now let's talk about the ideal sampling model. Okay. In the ideal sampling model, you've got a signal, again, x sub c of t, which could be arbitrary signal. It could be noise. It could be anything. That goes to a device which we'll call a C to D, continuous to digital. This is not the, this is kind of the ideal model of analog to digital conversion. Ideally, like you would do exactly what you think. You would measure those samples exactly, no distortions, anything that we're going to talk a little bit later when we talk about non-ideal case. So we're going to call it C to D as opposed to A to D. Okay? Just to differentiate between the non-ideal to the ideal. It produces samples every t seconds. Okay? And it produces outside of that system, out of that system, it will produce a discrete signal, which is the evaluation of the continuous time signal at n times t, at times n times t. N means an integer. Okay? So discrete to continuous. You've got this continuous, red, nice, beautiful line. You discretize it by evaluating that function at these points. Now, this is a two-axis thing. This is axis of t, which is axis of time, but it's also axis of n, which is indices. Okay? I'm just overlaying them, but n is just numbers, integer numbers, where t actually has a meaning, whether it's time, whether it's space, and so on and so forth. Okay? Now, if we want to model this, we're going to go through some translation layer. And we're going to create this virtual signal, which is non-realizable, but it's going to help us do a lot of analysis. And that beautiful signal is x sub s of t. It looks similar to x of n, but it's not the same, because x sub s of t is a continuous time signal that is impulsive. Okay? So we're going to define an impulsive sampling, basically multiplying our continuous time signal with a discrete train, with a train of impulse function, a comb function, a Shaw function, an impulse train. We're going to multiply that. That has a spacing of t seconds in between. Now the axis is the same. T is the same for both signals. Where here I have n and I have t. Subtlety, but makes a difference. Okay, so be careful. So x of s is the multiplication of the function, x sub c, by this delta train. And when you multiply with a delta, a function with a delta, you still get a delta afterwards that's weighted by the value of that function at that point of this impulse. Okay? If you remember from 120 or some other class that you took that has impulse function. What other class teach impulse functions? 20 dead, 16. What else? Most math classes teach delta functions. 126, 118? What is 118? Okay, Fourier analysis. Okay. The delta function is a weird beast. Okay, it's a weird beast. But it's really interesting for analysis. If you just think what the delta function is, kind of crazy, right? It goes to infinity, but has a unit area. It's like this weird beast. But intuitively, we kind of figure out, okay, like it's like the value at that particular point. Okay? I did this demonstration before, right? Like, right? That's trying to impulse response. You put an impulse. Right? Delta is like infinite, but like infinite value, but small, tiny. Okay. Think about that. All right. So x of s of t is the multiplication of our function with this impulse train. You've seen this before, right? You've seen this. That's great. So here's the ideal sampling model. Okay, we've got this multiplication with the impulse train. It's not physical. Again, we're just going to use it for modeling and derivation. And there's going to be a relationship between x sub c, x sub s, and x of n. X of n. All these have relationship from a mathematical point of view, and we're going to find those relationships. So the question is like how x of n is related to x of s in the frequency domain. What do you do? What do you do? If you want to figure out what the relationship to the frequency domain. Take the Fourier transform. Yeah, that's right. Take the Fourier transform. Do Spois. I'm going to show you a video of this, just so you see the culture. Okay. If I take so this is continuous time. So I need to take the continuous time Fourier transform, right? Right? Continuous time. The continuous time Fourier transform is an integral. But when you integrate over delta functions, you get values. And therefore, that integral becomes a sum. Okay? If you integrate over delta functions, then you get values at particular points, and then you've got sums. At the same time, this, x of n, is, if I compute x of e to j omega, is the sum of x of n, e minus j omega. And in this case, x sub s, j capital omega, will be the sum over x sub c, n times t. That's the points of the delta. That's the locations of the delta functions and their values, right? Multiplied by e minus j omega, capital omega, n times t. Okay? Because we're sampling it at points that are nt. So the relationship is quite simple. Basically, omega equals, small omega equals capital omega times t. That's it. That's the relationship. And it kind of makes sense because we're sampling at those distances, right? So yeah, it should be. I mean, the nice thing about x sub s, it has physical meaning. The physical meaning is that it has units. The units are seconds, right? Units are seconds, and those relate to frequencies which are hertzes or inverse radians, right? Inverse radians or radians per second, right? Right? So those relate, they have units. N is unitless. Hence, the frequency is going to be unitless. And so you need to have some normalization, okay, where this is normalized because this is second, this is radians over second, unit goes away. You just are left with a value. Okay, so it makes a perfect sense. Because we don't know, when we have x of n, we don't know how it relates to time. We need to know t if we wanted to know how it relates to time. Okay? So subtlety, but yes. So now when you display a digital signal, you can display it as a function of n, or if you knew what t was, you can present it as a function of t. And then when you compute the Fourier transform, you can show it from minus pi to pi, or if you knew what the sampling frequency is, you could also relate that to the actual frequencies that you sampled. Okay. Any questions? I'll let you go because it's basic. How is x of s related? now to x sub c of t. X of s is the impulsive measurement of x of t, x of c. So you multiply this with a train of delta functions. You've seen this before, right? This is an impulse train with an amplitude 1. Have you seen it written in a different way? Have you ever seen it's written like this? Have you seen this function? Okay, that's another. Okay, let me show you, because this is another way of writing it. So if this function, the Shaw function or the comb function, it's written that way, and they picked that letter because it looks like a comb function. It looks like an impulse train. Okay? You'll see this is very common representation. This function is really the sum of n minus infinity to infinity of delta t minus n. Okay? That's another way of writing it. Very common. So if you write that impulse train, but with a sampling at n times capital T, you can also, now how do you relate that to this? Because this is with, n times 1. So how do you relate this to this? Well, you can write this impulse train as delta of capital T, t over t minus n. This is exactly the same. This is the same as this. But if you know that if you scale a delta by t, then you have to divide up front. A delta that's scaled by t has to be divided. Like if you want to find a relationship to a delta that is not scaled, then you have to divide its value. And so it's kind of like you stretch something, you stretch something, then you have to scale it down. So delta of sum a times t equals 1 over absolute of a times delta t. So if you scale the delta function, you get that relationship. Hence, if you want to write this in terms of the Shaw function, you get 1 over t, capital T, Shaw function, t over capital T. But this has an impulses of amplitude 1. Okay? This has impulses of amplitude 1. Okay, that's another way of writing this, and it's very common in many, many books and papers and so on and so forth. So it's good to know that if you haven't seen this, this is another way of writing it. Okay, so how they're related. So S of t, which is the impulse train, has a Fourier transform. If S of t has an amplitude 1 delta function separated by capital T, that's the sampling rate. So S of j capital omega, you just do a Fourier transform of each one of these delta functions. Well, that's a problem, because if you do a Fourier transform of delta function, you get a complex exponential, and then you have to sum all these complex exponentials. And as it turns out, that's the beauty about this. It's actually not so easy to prove, but you can prove it that the Fourier transform of an impulse train is actually an impulse train. It kind of makes sense in a way that if you have something impulsive in time, it's going to be periodic in frequency. If you have something periodic in time, it's going to be impulsive in frequency, right? If you have something periodic, it has a Fourier series. Hence, its Fourier transform is going to be impulsive. If you have something periodic in frequency, well, who cares? I mean, Fourier transform is completely symmetric up to some constant. So if you just change whatever you want, and then you'll see that, yeah, it is going to be impulsive in time. So if you have something as impulsive and periodic, it will have to be impulsive and periodic, and just from that point of view. So the Fourier transform of this impulse train is actually an impulse train that scales to 2 pi over t. And the distance between those is also inversely proportional to what it was in time, right? Anything that is spaced a certain way in time is usually inversely proportional in the frequency. Whatever you stretch something in time, it spreads in frequency and vice versa. So the distance between these impulses are going to be 2 pi over capital T. Who has not seen this before? Done. So x sub s of j omega is going to be now, okay, so now you've got this, if you have a multiplication in time, you've got a convolution in the frequency domain. You've seen this before, so your convolution is going to be 1 over 2 pi x sub c of j omega convolved with this impulse train, which is s of j capital omega, which will give you your signal that is going to be now about every delta function, every impulse function of s of j omega, you're going to just put your signal around it. So effectively, you're going to replicate your signal around one of these impulses. Okay, so you got replication of your signal. And the replication is by omega sub s. Anytime you convolve with a delta function, you've got the evaluation of, basically, if you convolve with a delta function, you get back your function. If you convolve with a shifted delta function, you've got your signal that's shifted by how much that delta function shifted. Now, if you've got a train of these, you're going to get your signal shifted and added on top of each one of these delta functions. Hence, you got your self-replication. And a replication at a distance of omega sub s, which is proportional, of course, to 2 pi over t, which is your sampling rate. That's the sampling frequency, and that's the sampling rate. Who has not seen this before? How come your faces are so puzzled? What K? Oh yeah, there's no K. Should have put a K here, right? Nice. Nice. Good job. That's great. There you go. Would that work? Yeah. Is that right? What do you mean functional? It's not all right? Oh, you want me to regenerate it right now? No. Forget it. Okay, let's go to the list. All right. Remind me? Richard. There you go. So this, I'm quite at a loss here. Okay. Not too bad though. Not too bad. Not like previous years where hundreds of dollars. Okay. So here are how it works. Okay. Pay attention. Pay attention. Pay attention. Pay attention. Delta train. Delta train. Distance changes 2 pi over t. Amplitude 2 pi over t. Okay. So if x sub c, the Fourier transform of our signal, looks like this, with a maximum frequency of omega sub n, if the sampling frequency, omega sub s, is bigger than twice that frequency, or is at least as big as the bandwidth of my signal, okay, the full bandwidth of my signal, then I'm going to get a replication. I'm going to get a dude, one of these, over each one of these. And those dudes are going to sit one next to each other nicely. Okay, shoulder to shoulder, but not being disruptive. Okay? So x sub s of j omega, now this is continuous time frequency, where this is omega sub s over 2, or omega n, will look like this. If I actually put small omega equals omega times t, I'm going to get here pi, which makes perfect sense, because whatever was continuous now has to be periodic, because I sampled it. I have samples. If I'm looking at x of n, has a discrete time Fourier transform, which is periodic with pi. And this is your pi. pi correspond to omega sub s over 2. Yes?
But if omega s would be much bigger than 2 times omega n, it wouldn't stretch through the axiom.
If omega s will be much bigger than twice n,
There should be white space.
there will be white spaces. That's right. There will be white spaces between them. That's right. And they will be comfortably sitting next to each other like some of you. So here, omega s was pretty good. Here, over here, oh man. This is like huge omega s. Right? Space. Does this make sense? But I don't see the case where omega s is smaller than 2 pi n over here, because nobody's sitting on anybody's lap. Yet. Because if that would have happened, if omega sub s is smaller than 2 pi at 2 omega sub n, then you got yourself overlaps between the spectrum of each of these replicas. And that's when stuff starts disguising. Frequencies disguise or alias into other frequencies. Because frequencies which are higher are going to go and look like as if they're lower. When we look at pi to pi, you've got stuff here that originally was higher, now it's lower. And that's aliasing. In the case that you've seen before, it went all the way to 0. Could have been many times. Who knows? But could have been many, many replicas. But at least one replica that went all the way to 0 in that video. So does it happen? Absolutely. One of them is the videos that I showed you. Here's another example. This MRI. MRI, if you don't sample according to, so in MRI it's a little bit opposite. We sample in the frequency domain. Then we compute a Fourier transform, we get the image. I mean, it's the same thing, right? They're all symmetric. So you can think of it as the size of the object being the bandwidth, and the rate that you sample the frequency domain, right, is going to be dependent on how big the object is. That's the bandwidth. Hence, if I didn't sample enough, I'm going to get my nose in the back of my head, pretending to be. Because in fact, it's not there. My nose is in front of me. It's not the back of my head. But it's going to be disguised to my nose being stuck in the back of my head. Does this make sense? Now, of course, there's a way to mitigate with that. And if you want to take like 225E, I don't know, you'll definitely understand why that is. So you can mitigate with that. So, if I sample, if this is the frequency domain, where I actually make measurements, and I make measurements and I have a certain distance between these lines, that in that case is proportional to the size of the object, the size of the field of view. If I don't meet that rate, then I'm going to get this aliasing. Okay, overlapping. This is exactly the same. And does it happen in real life? Absolutely. Here's an example where somebody has this thing, this tube stuck in the middle of their abdomen. This is a cross-section through an abdomen of a pediatric patient. There's this tube that's stuck there. It's like, oh my God, we got to get it out. Well, it turns out that was an IV tube that was outside of the object. But when the tech prescribed the field of view, it prescribed a smaller field of view, which means that the sampling in the frequency domain was not as dense as it should have been to cover that. And that tube aliased all the way in and shows up as if it is in the object, but it's not. So that's why techs actually should put the tubes as close as possible, but they didn't pay attention. Okay, this is a typical thing. You have to worry about. So you have to worry about aliasing when you are an MR tech or radiologist. For some. Any questions? So clear.
just the widths of that you're sampling in space, correct?
In the frequency domain.
Okay, so now you're sampling in the frequency domain.
Yeah, it's crazy. It's crazy. MRI computes it's like a Fourier Transform machine.
Right.
It takes your head, computes the Fourier Transform analog Fourier Transform, and then you measure that. Isn't that insane? A machine that computes the Fourier Transform for you. Mind you, a lens will do that. Like a lens does the Fourier Transform of the image. If you look at the focal length, if you put a picture in the focal length of a lens and then you measure the other side, you get a Fourier Transform. Do you know that? It's crazy, right? And then you can filter it. There's all sorts of cool stuff. Like you can put like a slot, and that will filter the frequencies. Put low pass, high pass, stuff like that. You can do crazy. The problem is if you put an A to D at the focal length, the A to D will measure intensity, it will not measure phase, because the wavelengths of light are so quick. It's really hard to measure phase directly. Hence, you will get the magnitude of the Fourier transform. You will not get the phase of the Fourier transform, which then leads to all these algorithms that people try to recover phase from magnitude of the Fourier transform. And as it turns out, it is possible under some constraints. And then you do cool stuff like focusing, like capture data and then focus images on a computer from the data. You can do all sorts of really beautiful, what's called computational imaging, which maybe I'll have Laura Waller give a lecture in this class about that. But only if you're nice. Okay. All right. Moving on. So, how do we reconstruct? Well, everybody heard here about the Nyquist theorem. And the Nyquist theorem says that suppose you've got a band-limited signal. Band-limited signals are signals that are band-limited. Means that they have finite support in frequency. Does that signal actually exist? Like physically. Can you have a band-limited signal? Like physical band-limited signal. Like zero outside of a certain band. Non-zero inside a band. Can you have that?
Sure.
Absolutely not. Absolutely not. Mathematician will tell you. Because in order to have a band-limited signal, you have to have infinite time. You have to have an infinite support of a time in order to be finite in the other domain. That's it. But you could, from any engineering point of view, if something decays at a rate that's like insanely fast, yeah, it's band limited. Okay? So yes, from an engineering point of view, from a mathematical point of view, no. You have to have an infinite signal in order to be really band limited. Once you crop it, it's not band limited. Because you're going to multiply by a window, and then you're got ripples. Now, ripples can die quickly, but there are still ripples. Okay? Let me ask you, in MR, all you need is band limited in space. That band limited in space exists. Absolutely. Absolutely. Band limited in space exists because we're finite objects. Right? And so there it's actually the case that you've got band limited in space. But the resolution is infinite up to the atomic level. So, yeah, that's the difficult thing. Okay, let's move on. It's mind-blowing. All right, so if we've got a band-limited signal, that means that the signal is zero elsewhere. Then the Nyquist theorem says that as long as you sample at twice the highest frequency, then x sub c of t can be uniquely determined from its samples. So if you make the samples, you can go back to x sub c of t exactly, which is huge. That means that you can exactly store whatever is analog in the digital domain. Now, band limit is really the key to this uniqueness, because if you've got samples, and that is the original signal, I can come up with different things that would satisfy that. I mean, this signal will satisfy that. Right? That signal will satisfy that. This one will satisfy that too. But how do I know that so which one is the real one? As it turns out, the only one that's real one, if it's band limited, the band limit is the key to this uniqueness. If you don't constrain it to be band limited, then you don't have this uniqueness, because those signals are not going to be band limited by that value. Okay? They actually have much higher extent in the frequency domain. Hence, they're not the right one. So how do you do recovery? If you think of recovery, it's really easy to think of it in the frequency domain, because I can take a signal x of n, and I can convert that into x sub s by converting it into an impulse train. Okay? If I convert it into an impulse train, I got x sub s of t. So the Fourier transform of x sub s of t looks like this. So if I have a magic A to D converter that spits up with the right amplitude, with my samples over time, like that, that's my x sub s. The Fourier transform looks like that. If I want to recover back x sub c, what do? Low pass filter, just take this one. And, for mathematical point, I need to track the heights, so multiply by t. 2. So I'm going to multiply it by a ideal low pass filter. Hence, get back my reconstructed signal. Now, what is multiplying in the frequency domain by an ideal low-pass filter? It is a convolution with a... No, with a sink. No, it is a convolution with a sink. Confused you. And obviously, we've seen this before, right? So h of r of t is just the integral from minus omega s to t of t, and then you get a sink. I mean, come on, I'm not going to do it. I mean, you've seen this. Taking a rect and getting a sink out of this. I'm not going to spend time. Okay? The sink has zero crossing at times t equals nt, which is cool because there we don't have samples. Right? When we convolve this, we're going to get x sub r of t is going to be the convolution of x sub s of t convolved with this h of r. Okay? If you actually compute this, basically what you get is this is discrete, this is continuous, and now your samples become coefficients of shifted sinks. Your samples become coefficients of shifted sinks that are added together. So, if I've got these samples and I created this impulsive signal out of them, x sub s, all I need to do in order to reconstruct is place a sink around each one of them. And look, the beauty of thing is that they don't interfere with the other measurement. And then another one, and 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 so on and so forth. Until infinite. And then, when you sum all of these, you get yourself your unique signal. Questions? Now, what happens in the case where you have aliasing? What happens when you have aliasing? What if you have aliasing in the discrete signal? What are we going to be reconstructing? Something else. What we're going to reconstruct, in the case of alias version, what we're going to be reconstructing is we're going to reconstructing one period of this alias version. Okay, so if the spectrum of our sampled signals has aliasing in it, so it has these things in it, after performing the low-pass operation, I'm going to just be left with one replica of this alias version. So that leads to something that's very interesting. How can I even avoid aliasing in the first place? And I mentioned that kind of before when we looked, because I called it an anti-aliasing filter, right? And I'm going to I had a demo to show you. I'm going to show you on Friday. I'm going to show you the demo. I prepared it, but I need 3 minutes for this. We have 40 seconds. So let me just give you kind of a hint of what's going on. So if I have a signal and that goes through an analog anti-aliasing filter, you've seen this before. Like that's what we looked at. If I have a signal that is less, that the sampling rate is less than twice the highest frequency, then I'm going to get aliasing if I don't have this anti-aliasing filter. If I have the aliasing filter, I'm going to basically crop X sub c by that low-pass filter. So I'm always going to guarantee that it is band limited. I'm going to throw some stuff away, but it's still going to be band limited. Because I throw stuff away, now my signal is not going to have aliasing. But how well do analog filters work? It's hard to create an ideal analog low-pass filter. And it's the case when you have a signal that's its spectrum, and you might have something that interferes, or close by. And I want to digitize that spectrum. I'm going to run it through this analog low-pass filter, which is it's not going to be ideal. And when I sample, I'm going to get a few things. First of all, now the spectrum is a little bit distorted, right? Because it's not really cropped at like a rectangular. So now it's going to be waiting for the high frequencies. But also, some of that interference might leak. And it's going to alias into my spectrum. And I'm going to show you that next time with the SDR, because that's exactly what's going to happen. Now here's the cool thing about it. Once you have stuff in the digital domain, you might be able to take care of that. If you, for example, oversampled a little bit. So don't sample at the Nyquist rate, but sample a little bit more. Then you might be able to deal with all these analog domain distortions in the digital domain and correct for a lot of these, which is really extremely powerful because it's so hard to make ideal components. But once you're in the digital domain, you can actually create an ideal component. Well, up to a certain limitation. All right? With that, I'm going to see some of you tonight, and I hope all of you on Friday. Just hold on a second. Smile. Thank you.
Open quote, but no.
Which one?
Closed quote. The ones where you showed with the sync summing to the. That one below. I remember that quote. This one. Yeah. Open quotation.
Where?
The quotation mark.
Oh, nice one. Okay, I'll give you.